Hello. Today we're looking at Problem C from SCUDEM 2025, Birds of Different Feathers. It's all about how animals in mixed species herds detect predators. We're not just talking about more eyes equals more safety. We wanted to model how individual animals, say a zebra, decide how vigilant to be when surrounded by other species. Because vigilance isn't free. It costs time, energy, and foraging opportunities. So the question is, what's the optimal level of alertness for survival and fitness? In the wild, animals often group together, sometimes with their own species, sometimes with others. And one reason might be that different species bring different strengths. Maybe giraffes see better at long distances, or buffalo are more sensitive to sound. So when they herd together, they might detect predators more effectively. But there's a trade-off. Scanning for predators means less time eating. So each animal has to balance the benefit of staying alive with the cost of missing out on food. That's the core tension we modeled. To keep things manageable, we made a few assumptions. First, predator behavior is seasonal. Lions, for example, hunt more aggressively during the breeding seasons because their energy demands spike. Second, prey behavior is seasonal as well. During dry periods, animals cluster around watering holes, which affects herd density. Third, we assume herd composition reflects the local species proportions near a watering hole. And finally, we fix the distance between predator and prey. That lets us isolate vigilance effects without worrying about spatial dynamics. These assumptions helped us build a clean, focused model. We define an individual's fitness as G equals PF, where P is the probability that an individual of species J survives a predator encounter, and F is the fitness if it survives, basically how well it's doing in terms of energy and reproduction. We're trying to find the evolutionary stable strategy, or ESS, for vigilance. That's the level of alertness that maximizes fitness and can't be invaded by a mutant strategy. To find it, we take the derivative of G with respect to vigilance V and set it to 0. This equation balances the marginal benefit of vigilance, better survival, with the marginal cost, lower fitness from less foraging. Further breaking that down, let's look at marginal benefit. Vigilance reduces predation risk. We model survival probability as P equals E to the negative mu T, where mu is the instantaneous predation risk and T is the time period. So the derivative dP dV captures how vigilance lowers risk. More scanning means lower mu, which means higher P. Looking at the marginal cost, vigilance cuts into feeding time, where we model the energetic profit as E, where F max is the maximum foraging rate for species J, and C is the baseline energy cost like metabolism or movement. So, as vigilance V increases, the term 1 minus V shrinks, and energy intake drops. That's the cost in this equation. Plugging those marginal terms into our fitness condition, and after some algebra, we get something like this. This equation tells us the benefit of vigilance, how much it improves survival, has to equal the cost, how much it reduces fitness through lost energy. It's elegant because it links behavior, vigilance, directly to ecological parameters like food availability and predator pressure. Okay, now we're zooming in on how predation risk is calculated. Looking at the numerator, this is a scaled group size. N is the number of conspecifics, and alpha is the predator's preference for species I relative to species J. So if lions prefer wildebeest over lions, that affects how much risk zebras face. And in the denominator, this is the herd's ability to reduce lethality, where K is the baseline survival, like luck or agility. BV is the focal individual's own vigilance, and -1 times beta V is the vigilance from other zebras, and the summation is vigilance from other species. So the more vigilant the herd, the lower the effective risk, and the more preferred your species is by predators, the higher the numerator, and the higher the danger. This structure lets us simulate how mixed species herds dilute risk and share vigilance.
So now that we have a formula for mu of j, the predation risk, we can then take the partial derivative of that with respect to vigilance and set it equals to the loss in foraging with respect to vigilance. We then find the ESS vigilance as follows below, and we multiply m in the formula, which is the encounter rate of prey encountering a predator, by C of t, the predator breeding seasonality. The reason why we do this is that we can expect to encounter more predators during breeding season, especially because their energy needs are much higher to one, give birth, and two, to raise cubs. So here, we want to then find the optimal value for the ESS vigilance for each of the species in the current herd configuration. The way we do this is that we use the numerical method called fixed point iteration as opposed to an analytical method like the Jacobian because of the fact that it's more computationally intensive and also yields less accurate results, especially for a nonlinear system like ours. So the reason why we can use the fixed point iteration method here is that the criteria for using it is that the derivative of a function has to be between 0 and 1, bounded between 0 and 1. And ours fits the criteria perfectly because we have a cyclical function and vigilance is bounded between 0 and 1. So the way that this method works is that we first have an initial guess. So say the vigilance for each of the species is 0.3. We then use that as our current guess, v of k, and we plug it into the ESS vigilance formula, g. We then get the output vk plus 1. We then plug vk plus 1 and we use it as the next input. And we repeat this process 1,000 times or 1,000 iterations. So what happens is that after 1,000 iterations, we try to find the value vk plus 1 that minimizes the difference between vk plus 1 and vk. And we want this sort of difference to be less than 10 to the power of negative 6. Given that we now have the ESS vigilance, we can then find the probability that the herd detects a predator. And the way that we define that is that we define it as a probability that at least one individual in the herd detects a predator. So we use the formula above for total non-detection probability, and we subtract it from 1. So V of j is the species ESS vigilance, as we know, and we multiply that by p-scan, which is the probability that a species in the same time period that they're vigilant will be able to detect predators. We then take that to the power of nj, which is a scaled group size. So we define a particular effective group size, let's say like 12, and we have 7 animals in a hypothetical herd. We multiply the number of every animal in the given species by the scale factor 12 over 7 in this case, so that we can control for the dilution effect, which is essentially when we add more animals in total, the vigilance will go down. We want to calculate the quality that each individual animals contributes to the herd.
So this is our first set of model results. We graphed zebra vigilance as a function of time and looked at 4 specific cases: a case with just zebras in the herd, a case with zebras and giraffes, zebras, giraffes, and buffaloes, and zebras, giraffes, buffaloes, and wildebeests. We first investigated how the total size of the herd affects zebra vigilance over time, and as you can see, the vigilance of the zebras decreases as the total size of the herd increases. For each of the 3 graphs, the herd with just the zebras has the highest vigilance, and as you add more and more species, the vigilance decreases as a function of time. Each of the vigilance graphs are also periodic, which is determined by the breathing cycles of the lions in the savanna. We also graphed the probability of predator detection over time. As you can see, the probability remains unchanged as you increase the total size of the herd. This is because the effects of increasing the herd size and decreasing the vigilance cancel each other out in the probability detection equation. You can also see that in general, herds with more species have a higher chance of detecting a predator on the savanna. We also investigated some special cases where we modified the average risk of the environment. In a low-risk environment, the vigilance of the zebras is low, while in a high-risk environment, the vigilance of the zebras is high. Notice that in the low-risk environment, there's a sharp decrease in vigilance and probability of detection in certain time frames because of the combined factor of low risk and the minimum in the lion breeding cycle that creates this large effect. We also investigated cases where we modified the food abundance. In one case, we increased it by a factor of 5, creating a wet, lush environment. In another case, we decreased it by a factor of 5, creating a dry, harsh environment. In the wet, lush environment, the zebra vigilance significantly decreases, and this is because the zebras are focused on eating and foraging. Likewise, in the dry, harsh environment, the zebra vigilance significantly increases, and this is because due to the lack of food, the zebras are focused on looking for food and therefore looking for predators as well. So in conclusion, for almost all of our cases in our model, the vigilance of the zebras decreased and the probability of detection increased as more and more species were added to the zebra herd. We also saw that the size of the herd and total is inversely proportional to the vigilance of the zebras, while it also had very little effect on the predator detection probability. The periodic nature of the lion breeding seasons correctly results in a periodic vigilance levels and probability detection in the graphs of our model, and introducing special cases yielded expected results for environmental risk and food abundance. However, further improvements could be made to this model. The model could be expanded so that the vigilance of other animals could be calculated other than the zebra's own vigilance. Various additional periodic parameters could be added that would increase the complexity and nature of the results. We could add more predators to the population, including cheetahs, hyenas, and leopards. And on the savanna, probability of detection is determined by additional factors, including environment, time of day, bush cover, and random effects. These effects could be factored into our own probability equation in future results.